We are happy to welcome Carol on ninth Data Science UA conference. How are you? Hi.
Hi. Thank you for the introduction. Yeah, I'm fine in the current situation, COVID situation. Um, well, okay. So today I will talk about how to use computer vision methods for skin cancer recognition, and how well I'm doing actually skin cancer for about 15 years now. Analysis, data science, machine learning, and computer vision for health projects. Um, One of the topic that I studied and that well I wrote about it a few articles is about skin cancer, how to recognize skin cancer using machine learning and computer vision. Um, as in the introduction, I obtained a PhD in the topic of skin cancer recognition in 2015. If you have any questions, here's my email. Just drop me after the presentation, or uh, if if you want to stay in touch after the conference, here's my email as well. So, what is the current state of machine learning research in general? When I started my research in 2008, it was quite hard because, well, people didn't want to use any kind of machine learning methods. And the doctors were, I mean, the medical doctors were afraid that, well, AI will kind of replace them, or this kind of thinking. Now it's changed, and also the way of the researchers changed a bit, because the goal here is not really replace the doctors or try to replace the diagnosis with an AI. It's more about supporting the medical doctors in the diagnosis. And there are different solutions how to do it. One of it is obviously a binary classification, like it's a cancer or not a cancer. When we talk about skin cancer, obviously, and that's one of the case. Or we can have a multi-class problem, like we can classify between cancer and also different cancer, different skin cancers, because what melanoma is, well, it's the worst skin cancer, but there are different type of melanomas, and there are also other illnesses, skill illnesses, that we might be able to recognize. That's also a challenge that we need to face currently. The other thing is, well, using one of the scoring methods that medical doctors use. So they use, for example, the 7-point checklist, the ABCD scoring method, and there are at least a few different scoring methods they use on daily basis when they do the diagnosis of a skin cancer. So from the data scientist point of view, what we can do, we can automate these scoring methods. That's one of the possible solutions as well. Or what we can also do, we can also find patterns that are specific for example, for melanoma or other skin illness. For melanoma, we have more than 30 different patterns. There are even special books for that, the atlas of patterns, um, where actually you can find all of the patterns that are specific for melanoma, and also the patterns that are specific for uh, actually a non-cancer illness as well. So these are the possible solutions we can uh, implement to support the doctors. When it comes to the data set that is currently available for the research, when I started my PhD, when I started my research on skin cancer, I approached one of my colleagues at the university asking for a data set because he already did some research before on skin cancer, and I asked him to share the data set, and he actually gave me it without any problems. But when I counted the number of images, it was 53 images. So it was a bit weird. So I asked it if it's the old data set we have, and actually at that time it was all we had. Um, that's that's weird because having 50 images, more or less 50 images, it's something where actually you cannot really do a serious research on skin cancer. Um, so what I did, I actually spoke with most dermatologists. Uh, I mean, the ones that I actually met, many of dermatologists, and spoke and asked them to share the database that they have. Finally, after 1 year of work and talks, I was able to obtain a data set of 5,000 images. What is a good result. But now, if you want to start a research on skin cancer, you can easily download more than 30,000 images on the ISIC webpage, for example. And everyone can do it. I mean, it's public. So for the research, you can use it, and that's a huge improvement when it comes to the way how to do skin cancer analysis. And actually, this problem applies also to other health tech illnesses. Same with breast cancer, brain cancer, and so on. The problem is with the data set, and more and more institutions, hospitals are able to share the data sets for the research. So for now, we have a few. The most popular is the ISIC dataset that consists of 34,000 images, but also you have the HAM 10,000, or actually you have 10,000 images of not only cancers, but because you have also images of cases where you don't have a cancer, because you need to build the model obviously on different kind of cases as well. And two other less popular, MSK and BCN as well. So is it really used? So do the companies really use machine learning for skin cancer detection? So far, there are only two companies who really do it. So PhotoFinder, that's a German company that actually use, and you can download the app. You can download. You can actually use the app that they have provided for to use machine learning to recognize if it's a cancer or not. And the second company is Canfield, which is another company that just both actually are companies who in the past, and actually still, the core business is producing the dermatoscopes. That these are the devices that are used by the doctors to take pictures, for example. And what they do, they have implemented some machine learning methods to support the doctors. But there are more such companies that produce this kind of devices, and more actually introduce or will introduce machine learning methods. Um, just to show you how it changed during the years. So the goal of what actually was the goal of the challenges, because ISIC is not only a data set, they publish challenges every year to get the best accuracy, best quality metrics in skin cancer analysis. And between 2016 and 2018, the goal was more focused on feature extraction. So you can see it was more focused on the shallow methods here. So and that was actually something that I also did on my PhD. But since 2019, the goal is actually more focused on different kind of illnesses, and actually is mostly focused on deep neural networks, which is a bit different. The question if it's better, well, it depends, because from my point of view, a binary or multi-class classification, that's not the only challenge that we would need to solve, especially if you want to go and commercialize the solution. And you can see here that actually we are better and better when it comes to the way how we classify. Or here on the colors that you have here on the right are different illnesses. So the blue is the melanoma, but you have also some non-cancer illnesses as well, or different other cancers, skin cancers here mentioned. So you can see some of the cancers here, some of the illnesses still need to be improved, especially melanoma, which is not so bad. I mean, the blue line here, but still we still want to have better accuracy, better sensitivity when it comes to melanoma classification. When it comes to research papers, obviously that the information about 2020 isn't yet I mean, it's not a full information because the year is still we have still 2020, but you see there is a growing number of research papers in this topic, and it will increase. Now it's actually kind of a boom in topic of AI or machine learning in health tech, in diagnosis based on images, and that's something that we will see in the upcoming years. So the challenge, just to summarize this section, the challenge is here to support the doctors, the medical doctors, especially the general practitioners, so the doctors that are not specialized in dermatoscopy, because the accuracy, the sensitivity of such doctors is on a level of, depending on the research, but it's more or less about 65%. So that's quite low, and that's something that we should think about in the first place to support this kind of doctors and help them to increase the sensitivity. What's else? Sorry, that was my daughter. Um, what else? What we should do? We should extend the research not only on skin, because melanoma, the skin cancer, happens not only on skin but also on eyes and nails as well. So that's something that is more advanced. That's something that is not so popular. I mean, when you compare to different illnesses, eyes and nails, cancer, melanoma isn't so popular. That's good. But on the other hand, the data set, getting such a data set is much more difficult. Okay, so I mentioned something about the commercialization of such a product. We are now in a process of commercialization this our solution in skin cancer diagnosis. And the thing here is that apart from the machine learning part, computer vision part, what you need to face, what you need to have in mind just from start is the FDA that will actually approve your product as a medical product. And there are different levels that you need to different levels of clinical evaluation you need to have in mind, and that this actually takes time. Why I'm saying that? Because I would like to show you how it is important to think about it from the beginning, because many researchers, when they start doing skin cancer analysis, they do less computer vision methods. They use less feature extraction method with computer vision. What they do usually, they use some deep neural networks that will not be in most cases approved by the FDA. And the process of actually getting approved is really complex. It takes about 2 years to really go to the market if there are not so many issues. And why I mentioned about the FDA, because we should think about the methods to be explainable in the meaning of for the FDA, that we know what's going on, what happened with the image in the method to get the prediction. And why we actually use explainable AI. So for our case, it's about the regulatory agencies, because they certify the product. So that's one of the reasons why we should think about it. And that's why we should use the feature extraction methods, the shallow methods mostly. Not only, I will mention it in a minute, but in many cases, that's how you can obtain a explainable model. And there are also other reasons why you use explainable AI in health tech or fintech as well, because that's also a regulated industry. So obviously the domain experts, they want to know, the doctors want to know what actually is happening there. So why is it a cancer classified as a cancer, or why it's not? Obviously the experienced ones, they will know, but the unexperienced, like the GPs, they might have problems with figuring out why it's a cancer or not. That's why they have only 65%, around 65% of sensitivity in finding melanoma. Um, what else? Obviously, the regularity that I mentioned, managers, data scientists to understand how does it work in the back, and obviously the patients at the end that are affected by this case. And there are plenty of at least a few ways to explain it. Obviously, with some equations, with some tags, symbols, formulas. Uh, the best possible way is obviously using some visual explanation because that's easy to understand by humans. If it's a complex solution, you can use also some local explanation or simplify it. Simplify it, just make the whole problem present in a simple way to explain it. Or also very important way the feature relevance, because some features might not be so important for the classification than the other ones. But that's something that it's a part of the data pre-processing as well. So here I have two examples. Some of you might not don't know which one is actually a cancer or not. So this one here, it's not a cancer, or it's not a cancer yet. And this one is a cancer. I'm studying for 15 years now, so I can just take a look on the image and I know what if it's a cancer or not. There are some patterns here specific. Here's you have the network here. That's a kind of a network net here that is specific in many cases um, for a non-cancer case, and it's quite regular. When you see here on the other side, you have some dots. This is the dots here. This is specific for cancer, and it's super unregular, asymmetric. You have the blood vessels here as well, visible. You have the stripes. So that's an advanced case of cancer. And the patterns that I mentioned here, that is very important to find out from the image how to get the patterns visible. And just going back to the explainability, what we use white box models mostly. So it means it's not a black box. I mean, we know exactly how the model is built, what are the decision made. For example, a decision tree is a white box model. I mean, in most cases, because it's easy to replace with switch statements and clear to explain. And the black box, obviously, it's something that you put something in it, and it's hard to find out what's there. Another example of explainable methods, obviously, linear regression, decision tree, logistic regression. Most of the clustering methods are explainable as well. Yeah, decision tree again, or SVM. Even it's a bit complex because we have the Lagrangians multipliers in the back, but still, it is at the end it's a linear form that is quite easy to explain. So just to show you the differences here, let me show you the difference between black box and white box methods. Here we go. I hope you can see my screen now. So this is our very short, quite short network here. I mean short, small one, just 3 layers here, developed in Keras for MNIST classification, something very classic. And after the training, I get the network where actually I can print the weights in the layer. In this case, I'm printing the layer 2 weights. And as you can see here, these are the weights. A lot of numbers that are not really possible to explain what are the numbers, what does the number means. That's something that we consider as a black box method because that's very hard to explain. On the other hand, you have the scikit-learn decision tree classifier in this case, and the iris, also a classic problem. And after you build a model, it can be printed, it can be drawn like a tree like that. Even if you don't know what's x2 as a feature or x3, it's easy to explain what is the process here to get the prediction, right? And that's the basic difference between black box and white box method. Where actually the black box, most of the deep learning methods are black box methods. So how to make actually do how to do machine learning skin cancer prediction without deep learning? Well, you can do it. You can do it using some explainable methods like the models agnostic methods that are based on different kind of factors, like for example the feature influence, where actually you test the features that are going in and as input to a network, or based on the output, right? You try to explain a method based on the output with different kind of exercises. Or what you can also do, you can take a layer of a neural network and try to extract the features from a layer, right? So I showed you that a list of numbers. So try to explain these numbers, and that's a very hard thing. Um, but there are some types of neural network method where actually it is possible. When it comes to the feature influence, there are different kind of plenty actually of methods where you can test the method, the explain the black box method, just based on the features and the feature influence. There was a really nice book on that, like explainable AI. If you want, I can share the link after that. It's not my book, but it's a really nice one about agnostic models, agnostic methods, where all of the methods are explained in more details. The second type, based on output. So we have the SHAP methods, the Lime. You have also Python libraries just exactly for that actually implements this kind of method to explain the black box methods. Another one that is based on on a narrow network, so the third type of explainable of model agnostic methods are based on convolution neural networks, where actually we are explaining the classification based on it's called class activation map, which is a heat map. Then we are calculating the gradients on one of the layer. Usually, it's one of the last layer, and trying to find out what of the features are the most important. And on the image, it's easy to show using a heat map, just combining two images and show that actually in this case, the dog, it's actually this image. On this image, we recognize a golden retriever dog based on the ear, eye, head, and the chest, right? And depending on if it's a cat, if it's a car, you will see different regions that are found here. For example, here you have the kid, the cat or the Maltesian dog, and different kind of features are important on the image for classifying it as a Maltesian dog or a cat. That's something that you can do on a convolution neural network, and that's acceptable by FDA. So you can use a convolution neural network on images, and using this explanation, this will be approved by the FDA if you want to go with the product on the market. Okay, so well, let's move to the main part of the presentation. Let me show you how we did one of the methods that we have used for skin cancer recognition. So what we have done, first of all, is to choose the right data set. And the data set that I have showed you before, all of them, all of the data sets, the ISIC, HAM, BSK, and so on, they use the classic dermatoscopy images. What means they use, well, the visible wavelength of light to take the image. And what you get the regular dermatoscope image. And that's fine for most cases. But what we did, we have used one of the dermatoscope that actually it used different wavelengths of light. It used, for example, infrared, UV, and so on. So having more wavelengths of light make it make well it different cells react to different wavelengths of light. It means we get different images, right? So the collagen layer, for example, well, actually we use the UV ultraviolet light here, or we use the infrared, and there are different type of infrared images. Here's one, here's the second one, and there's another layer which is a combination of few. So a dermal melanin layer. So we have 5 images of each case, of each mole. And this gives us a better understanding not only what you see on the typical image, but also what's in it, what's happening here in the cells in the skin. And this gives us better understanding, more information, and a better, more precise, make it possible to build up more precise method, classification method, obviously. Um, so what we did, we checked the different scoring methods. So we have this kind of hunter score, 7-point checklist, A, B, C, D, E, and so on. And we choose the one that actually can be used on multispectral images. So the one that is used on multispectral images is the hunter score. So we try to automate, to find patterns that are available, that are in the hunter score method. Here I have some examples. Here you have, this is for example a brain pattern. Here's the blue veil pattern. That's a pattern that is specific for a super advanced cancer. It's kind of a blue, as you can see, kind of a blue-gray here in the middle. It means that the cancer is really deep in the skin. And that's bad because in the case of a skin cancer, people are not dying because of skin cancer itself. They die because of the other cancers that are, well, because of the skin cancer that isn't really that you didn't have done anything with the skin cancer, it's in already, the cells are in the blood. It means that you will get a different kind of other cancers anywhere in the body. That's why the people also affected by the skin cancer. So people not dying by the skin cancer itself. That's why it's important to take an action in the early stage. So we have here some blood here, concentration, blood vessels as well. Here you have the dots. You can see the white dots here, right? And here the darker color here, the deeper it is in going into the skin. So these are just to mention just 6 patterns that are specific that we can find out if on the image. So what we did, we have done some pre-processing. We use some pre-processing method. Let me show you these. So first of all, okay, let me show you some notebooks. Here we go. So first of all, what we did, this is actually, as you can see, I just used the ISAC because I cannot really share the other database, but that's not a problem. The moles are very similar when it comes to the first layer. What the first issue that you will face when it comes to data pre-process, the images that you need to handle is the border. And there are different kind of images. One of it is where actually you have dark parts around the mold. Like here, what you need to do, you need to just cut it and make this image make the rest of the image like kind of a skin color to really skip this actually in the analysis in the next stage. What you also have here, and you can do, is for example the hair removal. And there are different methods to already implemented to remove hairs. Obviously, it depends how many of what is the percentage that the hairs covers the image, because well, if there are too many, it would be hard to really find out what's actually behind it, what's actually the mole on the image. So that's one thing what you can do. Sometimes there is some shadows as well, or because the device, like the dermatoscope, isn't really, it's flat, right? I mean, the lens is flat, so it means if you put it on your skin, some of the on some skin, you can actually push the device, and it will be also flat, so there is no light coming from outside, and that's fine. But in some places on your body, it's very hard to do it, and then you will have some kind of a shadows that you also need to pre-process. That's also something that we do, but that's the most basic one here. So the border removal. The other thing that we also do, a second, just to switch to another notebook. Here we go. So is the color presence. The color presence. What does it mean? As you saw on some of the other images that I showed you before, there are different colors that actually you can see here on the image. So obviously you have the skin color, right? You have the, let's say, the dark, I mean the brown color, you have the black color, you have the light brown color, you have the red color for vessels, blood vessels, for example. And what is very interesting in case of skin cancer, the one of the most important color is actually the blue color, or blue gray kind of, like you can see here, right? So you can see here it's kind of a blue gray, and that means it's very deep. That's where actually you see it as a blue gray, but it means it's very deep. It means it's a very advanced. In most cases, it's a very advanced cancer, like here. So what we do, we obviously analyze the colors, build a histogram based on that, change also the color model, because the red, green, and blue model is not always the best one. So we have tried different ones like the HSV, for example, and other ones as well, and have it tested just to show, okay, what are the most typical colors here, just from one layer here, or just group it. Right? In this case, it's 10. But if you're talking about skin cancer, we talk about actually at the end 6. We mention about 6 colors, so we can obviously switch it to 6, to the 6 most important, and try to find out if we really have blue color there, or what is the most dominant color. The more color you have, the more colors you have on the mole, the more well, it depends obviously on the scoring method. But when we talk about ABCD, the more colors you have, the more advanced the cancer might be, because it doesn't need to be a cancer, because they are just color is just only one of the features that we have. So what we also do is asymmetry. Here we go. Asymmetry. So there are different ways how to measure the asymmetry. One of the examples actually divide what the doctors usually do. They divide it by 8, right? Eight pieces, exact same pieces on the image, and try to find out if the piece of the on the other side, on the opposite side, is exactly the same, like we have on the current one, and it's going just by the circle around and find out the symmetry. There are also different ways of measuring symmetry. I will show you another one in a minute, but that's the way how to find out if if it's a cancer or not, because symmetry is one of the first one of the first feature that, apart from color, that doctors are taking a look at, or trying to find out if it's a cancer or not, because a cancer is usually asymmetric, right? So it's not circle, it's not oval, it's not. It's something that is asymmetric, very asymmetric. Here have some other cases here, and what we do, we go through and check the symmetry just by finding out based on symmetry factors, right? In this case, so you can find out these numbers obviously reflect to each of the part of the of the image, because we divide it into some sections like here. So depending on that, we can find out if it's a symmetric image or not. And that's only one thing. Or the border shapeness, for example. That's another feature that is also important when it comes to skin cancer analysis. So shapeness, it's different than asymmetry, because it might be a symmetric image, I mean symmetric mole, but the shapeness, right? The shapeness of the border might be it might be smooth or not. The less smooth it is, the more probable it is a cancer. right? When we talk about A, B, C, D, E scarring method, so A is for asymmetry, B is for border, C is for color, D, depending on the metal, where on the paper it might be diameter, so the size. So we talk about 6 millimeters as the size. Below it's fine, above it's not fine, but that's not really a good factor in my opinion. In some research, in some other research papers, you can find that D is actually stands for differential structures, and E stands for evolution. So how did is there more changing in time? So B is border shapeness. So how what is the shape? What is the smoothness of the border? And what we do, we take the border here, right, and try to find out, okay, how many of these dots we really have here, right, on different levels. The less we have, the more, the better for the patient, obviously. And there are obviously some other some other researchers here with some images examples how to measure the shapeness. Oh, you can see here also some images with nails in this example, right? So that's something that is much more difficult to um, to explain. Okay, just let me show you some other examples. Here we go. Apart from some basic methods, what we do, we are able to find about 12 patterns now, like the blue veil, obviously the border shapeness, and so on, globals, stripes, and so on. So that's something that we are already able to find out. So we are able to cover the full hunter score. Um, Obviously, not we don't include the age of the patient because that's not something we can find out based on the image. But that the rest, the patterns that are mentioned in the hunter score, we are able to cover. We are already able to cover, and we actually moved up actually beyond that. What's more, we have found two other patterns during our research that might be correlated with the skin cancer that wasn't really mentioned in any paper before. So another way how we use that, another way how we found the shapeness or found a feature that is giving a better understanding if it's a cancer or not, is based on fractal methods. So we measure the shapeness, or the shape of the mole based on fractalness, on box dimension, for example. Lacunarity, box dimension, different kind of methods because there are different fractal methods, obviously. But one of it is the box dimension and lacunarity that we have used. And you can see here how is it changing. So how many boxes are filled with this image. Obviously, if the box is big, then there is no there are not really clues here, but the smaller the boxes are, it will change. So the line will be the slope will be different, but depending on the mole. As you can see here, if we just zoom on it, this is the one of the case that I showed you that is not really not a cancer, but that's a cancer, right? And you can see the shapeness here, the fractal, the box dimension will be totally different in both cases. So what we have used so far, we have used the SVM methods, we have used the decision trees, we have used also some neural networks, we have used convolution neural networks so far. If you go to ISIC and take a look on the methods that were used for skin cancer recognition, there are many deep neural networks, which is good, but it's not really so useful for commercialization in most cases. So that's what we use, and we are successful so far. So it will be commercialized probably in about 2 years, because this is the time that is we need for finishing the certification. Yet, where to go next? Just a few papers that I have published. Feel free to read. It's more explained from an science point of view in more details. The one of it is actually published in 3 years ago. It's about the fractal method that I showed you before, based on multispectral images. Uh, well, that's a really nice one when it comes to covering the hunter score method. Also, neural network in the semantic analysis of skin cancer images based on typical dermatoscopic images. And there are more of papers that I can recommend you that I have published. Just Google me on Google Scholar, scholargoogle.com, my name, and there will be a few papers that are about skin cancer. All right, that's it from my side. So I hope you have some questions. Here we go. Any questions?
So basically, we can check the chat, and we don't
Mhm.
have questions yet. So thank you very much for this presentation. It was really amazing.